About the angular harmonic motion for torsional pendulums and physical pendulums last time, with the concept of the approximation that small angle or small amplitude oscillations of physical pendulums consist of harmonic oscillations. So let's take it from that point onwards today. After having seen various spring mass systems and application of simple harmonic motion in that, it moved on to physical pendulums and torsional pendulums. So let's pick up some examples of physical pendulums. We saw that in general, if we have any rigid body which is suspended from a point P such that there is an axis through P, which is a fixed horizontal axis. Okay, for this body of mass m and moment of inertia IP about P. So if the center of mass is vertically below P, then this is the mean position or the stable equilibrium position, because the net torque is 0. Okay, but the moment we take the whole system to a position where now the center of mass is not vertically below the axis, so you can see that the weight creates a restorative torque. So if we have given it an angular displacement theta like this, we can see it will have an angular acceleration alpha like this because of the torque. So we have, so mg d sine theta becomes ip into alpha, where alpha becomes minus d2 theta by dt square, and sine theta can be approximated as theta for small amplitude oscillations. So small amplitude oscillation means that theta's maximum value should be less than about 5 degrees. So in that case, we get this relation that d2 theta by dt square is minus mg d divided by ip into theta, which is the angular harmonic motion equation. Okay. Omega square is, so time period now has the standard formula. So let's start with a couple of examples of the application of this. Just go through this once. This is a recap of the last part of the previous lecture, but in case there is any doubt with anything to do with this, we will discuss. Okay, so assuming that everything is fine up to this point, let's do an example. So typically in these type of questions,
can you scroll up?
Yeah, just. Okay, this is fine now?
Yes.
Okay. So typically the thing is about being able to apply your rotational mechanics properly to find out moment of inertia and all these things. So let's look at an example. So in our next example, what's going to happen is we're going to have quite an interestingly shaped object. We are using two rods to make a T-shaped pendulum like this. Okay, then it has a fixed axis through this point P, perpendicular to the plane of, so it can rotate freely like this. So this T-shaped rigid body consists of a rod of length 2L attached to another of length L at its midpoint. With this angle being 90 degrees as shown. Both rods are of same isotropic material and same uniform thickness. Now this T-shaped body is hinged at P such that it can rotate freely in the vertical plane of the diagram. That is, axis is perpendicular to the diagram. Okay. So you have to find the time period for small oscillations. Small oscillations typically means that small amplitude oscillations. So in any type of situation of physical pendulums, you'll always see small oscillation word being used. Okay, so we have to find the time period for small oscillations. So small oscillations means that the amplitude is small enough, the angular amplitude is small enough to be able to apply the small angle approximation, that sine theta is tending to theta. So as you can see, this question is all about rotational mechanics, actually, nothing else. Rotational mechanics, bit of center of mass concept. Okay. Just try to figure this out, we'll discuss. So two things you have to do successfully about the question. One is the moment of inertia of the whole body about the axis through P, and the axis should be a horizontal axis coming out of the plane or perpendicular to the plane of the diagram. And the other is to be able to locate the center of mass. And notice the total mass of the T shape is not given. And the reason for that is that will not be required, because you will express moment of inertia and mg in such a way that the common m term will cancel out, where m is the total mass of the object. So you can, for example, just consider a uniform mass per unit length or linear mass density lambda. So you can write the total weight in terms of lambda also, and the moment of inertia also in terms of lambda. So when you calculate time period, that lambda will cancel out. Okay, so I'm working out the calculation. Aman, there will also be a G term. Okay.
Yes, sir. मेरा calculation yesterday.
G and L. Okay.
Actually,
Yeah. Okay, so for example, if I take the linear mass density as lambda, okay, then making use of that for the center of mass thing, what I can do is suppose I take lambda L is equal to M, suppose. So then this part is having a mass of 2m at a distance of L from this, and this part is having a mass of m at a distance L from this. So the center of mass of the system now will be somewhere here. This will be the center of mass, and you can see that this distance will become L by 3 because the ratio of these two masses is this. Okay, so now the distance of my overall center of mass, the overall system center of mass, yeah, so the overall system center of mass will be at a distance of 4L by 3 from the point P. So that distance will be 4L by 3. And the weight acting through this point will be 3 mg actually, because we have taken lambda L as m. Okay. So now my omega square is going to be 3 mg into 4L by 3 divided by moment of inertia above that point. So now moment of inertia over that point P is going to be 2m 2L square by 3 for the 2L rod plus ml square by 3 plus m into 2L whole square by parallel axis theorem for the L length rod. Okay. So IP, to take ml square common, it's 8 by 3 from here plus 1 by 3 plus 4. So that will become 13 by 3. So I'm getting it as 7 ml square. Okay. So my time period but remember m is the total mass, so I should replace it.
sir, it will be ml square by 12 plus m into 12 square.
Yes, sir.
Oh, sorry. Yeah. This should be ml square by 12. ICM is ml square by 12. Okay, so 1 by 12 plus 4. So this term will become different.
So 81 by 12.
81 by 2.
So 4 plus 1 by 12 is correct now, no?
Yes.
So 32 plus 49. It gives us how much? 81 by 12. This is the answer you are
Yes.
getting? So 81 by 12 will also reduce, na? It will become 27 by 4. Right?
Yes, sir.
Okay. So square root of 27 by 4 ml square divided by 3m into g into 4L by 3.
Yes.
Just verify it, but 27 by 4 into 1 by 4. So this is 3 pi under root 3L by G. And also hope sure all of you understood in general the method and the concept in these type of questions. Oh wait, this is by 2. Okay, so I think this should be the correct answer. Just check the calculation while you're noting it downwards. But more important is the concept. Okay, so essentially physical pendulums is all about applying your moment of inertia concept correctly and center of mass concept correctly. Okay, people. So hope this is clear to all of you. Now moving on to one important variation for pendulums is something like this. If you have a pendulum inside a non-inertial frame, then how the acceleration of the frame and therefore the pseudo force, how it affects the time period. So we start with a very simple example. Suppose you have an elevator which is accelerating upwards at g by 5, let's say, okay. And we have a physical pendulum which is in the shape of a thin uniform rod like this, hinged like this, of length L. So first of all, show the equilibrium position of the rod with respect to vertical. and find the time period for small oscillations. So you'll see here, because the acceleration is upwards, this is a vertical uniform acceleration. So still the pseudo force will not be affecting the orientation of the rod in the equilibrium position. It will be vertical only. Okay. So the equilibrium position will be vertical only. We'll just do this question quickly. Next one, I'll give you some time to solve more interesting question. Okay. So in the non-inertial frame of the elevator, which is going up at A0, the force is acting through the center of mass. Remember, pseudo force will also act through the center of mass only. It will be like this. Okay. So this is the equilibrium position. So when we take it to an angular displacement with respect to the mean position, this net force, which is the vector sum of pseudo force and this thing, this will together provide a torque like this. The rest of the things are simple. Okay, so torque is equal to I alpha. So we have mg plus a naught into L by 2 will become ml square by 3 into minus d2 theta by dt square. L by 2 sine theta square. Yes, it's correct. So sine theta we'll take as theta for small oscillation. Okay, so we'll get d2 theta by dt square is equal to minus of 3 by 2 g plus a naught by L into theta. Or so omega square is this. So the time period will accordingly come out to be different. Okay.
Five L by 9.
Oh, sorry, I have reversed it. 5L by 9. Okay, so this is a simple example of pendulum in an accelerated frame. Now, next we'll see when there's horizontal acceleration. So then this part of the question will make more sense. Okay, so we'll take the same diagram, but this time we'll treat it as if the whole situation, instead of it being an elevator, it's a vehicle which has horizontal acceleration. Let's give it a quite a dramatic value of acceleration. 3/4 the value of g. Now let's find the time period. So again, we have to show the equilibrium position of the rod with respect to the vertical, and Just assume that this is long enough. So okay, just try this out, people. Okay, so what is the equilibrium position? It is 53 from the vertical, is it? I think it should be 37. Okay. Tan inverse A by G should come out to be. Anyhow, so let's see. So at the equilibrium position, people, this is what we'll see, that the vector sum of pseudo force and mg should pass through the hinge point. Okay. Or the torque due to mg and the torque due to pseudo force should cancel each other. That's another way of expressing it. Okay. So now remember, always in a uniformly distributed mass, just like gravitational force acts through the center of mass, like that pseudo force also acts through the center of mass. So if this is the equilibrium position, so net torque should be 0. So if this is with respect to the vertical way angle, taking the angle as theta, then mg into L by 2 sine theta is creating a clockwise torque. That has to be balanced by this, which is creating the anti-clockwise torque. So let's take this angle as theta naught, okay, so that understand is the equilibrium position. So equilibrium position is this, or 37 degrees with respect to the vertical. So you can also understand that this is becoming like, it's becoming like an effective weight. So you can think of it like this, that the vector sum of mg and ma like so this will really help simplify solving of the second part of the question. So there what we are doing is, suppose from this equilibrium position, suppose we are now taking the rod to a position where has an angular displacement like this, theta, then it's like the effective weight will be acting through this point. Now that will be an arrow that is acting parallel to this line. So you can see that it will have a moment arm, which is L by 2 sine theta. So at theta equal to, in fact, let's write this as delta theta. Theta naught plus delta theta. So we get okay. Anyway, so hope this is clear. Yes, very good. Naman, that is the value of omega. You can also write this as now 4 pi under root 2L by 15G. But the important thing is, again, you can see that the easy way to do any situation like this is to replace the vector sum of pseudo force and weight, like an mg effective term, which acts along a line, along an axis which is parallel to that equilibrium position axis. So therefore, it acts along a direction at 37 to the vertical in this case. And even this diagram and all this was then to explain it to you. Once you have understood the concept of G effective, you can just think of it like a regular physical pendulum, but just replace G with G effective and replace the vertical position with that position where theta is equal to theta naught. Rest is the same derivation. So this is one important variation for pendulum based problems, which basically checks all your concepts of mechanics more than anything else. Moment of inertia, center of mass, pseudo force, all these concepts together get tested out.
Sir, can you please show the question once?
Yeah, sure. So the question was like this, that you had this thin uniform rod, acting like a physical pendulum, but the whole system is inside a vehicle, let's say, or a reference frame that's accelerating horizontally, right, at this value 3g/4. So we have to find out two things: the position of the mean point or the equilibrium position with respect to the vertical. That means in this case, angular position with respect to the vertical. And the other thing was the time period for small oscillations.
So can you repeat the G effective part?
So see the vector sum of mg and ma. See the vector diagram that I've drawn over here below. Pseudo force, irrespective of what the position of the pendulum is, right? So irrespective of whether the pendulum is at rest at the equilibrium position inside, or you have disturbed it from the equilibrium position and it's oscillating and it's at any stage of its oscillation, pseudo force remains a constant value, no? Unless we change the acceleration of the body.
Yeah.
And mg is of course constant. So their vector sum is a sort of diagonal force, and that acts at the center of mass continuously. You understanding the point, no?
Yeah.
So that becomes like an effective weight of the object. Now, in this kind of frame, an object's effective weight is no longer just the gravitational force. It is a vector sum of pseudo force and this. For example, if you were to drop a particle inside this frame, in this frame, its acceleration would not be g. Its acceleration would be that g effective. Just like the free fall acceleration has also changed. Understood? So that is the concept of the effective g.
So torque, the force always has to be perpendicular.
नहीं तो देखो अभी क्या हो रहा है, when I'm at this equilibrium position, which are not shown in this diagram, but in the diagram on the left for the equilibrium position, you will see that if you were to draw the vector sum of ma and mg, that mg effective would lie along the rod, no?
Yeah.
So it does not have moment arm about the point P. But now imagine from that equilibrium position, so that equilibrium is at theta naught. Now I've given it a further angular displacement of delta theta. So theta is theta naught plus delta theta. So now you see your mg effective is still acting through the center of mass, but is its line of action passing through the suspension point? No,
No,
because it's parallel to this line, the equilibrium line. Understood, no?
Yeah, got it.
So it's just like your regular physical pendulum, but in your regular physical pendulum, what the role played by the vertical axis, now that role is played by this axis, which is at 37 degrees, and the role played by mg, now it is played by that mg effective.
Yeah.
So then it just becomes like, it's a regular question of the physical pendulum. Omega square is equal to mgd divided by ip, but just replace g with g effective. Okay, rest everything else will remain the same. And of course, geometrically, the difference is that the equilibrium won't be at the vertical position. The equilibrium will be at this new position.
Yes.
Okay, so that is the like a nice sort of shortcut trick way of doing these type of questions. Okay. Now we come to another type of angular oscillation. This time an angular oscillation where the restorative torque is produced by spring force. So sometimes you can also call this spring pendulum, spring-based pendulum. Okay. So there are different ways of naming these things. So for example, I think in your module, they are not calling it physical pendulums, whereas it is called compound pendulum. So compound pendulum and physical pendulum are more or less the same thing. Okay. Torsional pendulum is where you have a torsional wire. So like that, spring pendulum is any pendulum system that is there is got to be angular displacement and angular oscillation, but the restorative force is provided by spring. Okay. So now imagine the situation that this rod is actually in a horizontal plane. Gravity is going into the plane and it's hinged like this at the point P on a smooth horizontal surface. So this is a rod hinged at P, okay, on a smooth horizontal surface. So acceleration due to gravity is into the plane in this diagram. Now what we are doing is, let's say we have got on both sides at the other end point, we have attached two springs, which in this position are at their natural length. So the springs are oriented perpendicular to the rod, and both of these springs have the same constant K, and they are both at natural length in this situation. Again, we have to show that if we give the rod small angular displacement, it will perform angular harmonic motion, and we have to find the time period. So rod's mass is m and length is L. Okay. So show that for small oscillations, the rod performs angular harmonic motion. And find the time period. So just quickly take down the diagram if you like, then we'll discuss. So what we'll do is, again, you'll see that we have to somehow use the small angle approximation. So this time from this equilibrium position, which you can see because mg is going into the plane, normal reaction coming out of the plane is balancing it. And the springs are both at natural length. So there is no net force because of the springs. So the whole system is in equilibrium. But if you rotate it by an angle theta on either side, you will see that the spring forces will create restorative torque. For example, if you twist it, let's say anti-clockwise, then the spring on the right will be compressed and the spring on the left will be extended. So they will create a clockwise torque. Similarly, if you rotate it clockwise, the two springs will create anti-clockwise torque. So it has the property of restorative torque. Now the next thing you have to show is that if we make a small angular displacement, then that restorative torque is not only there, but it is actually proportionate to angular displacement. So small angle approximation will have to be used. And that proportionality between the restorative torque and theta, that equation will finally give you your value of time period also. So just try this out now from this position. Give it an angular displacement of theta and see how the torque is working, and then apply the approximation that theta is small. So if theta is small, then use the small angle approximations like sine theta is tending to theta and cos theta is tending to 1. Aman beta, यहाँ पे mg will not play a role ना, because mg is into the plane and normal reaction is coming out of the plane and it's cancelling ना. So had it been a vertical situation, then yes, but this is not a vertical situation. Yeah, Amog, you have got it correct. Okay. So basically, see, from this position, from the vertical position, I mean not the vertical, but from this position along the y-axis, if we take it to an angular position theta, like this. Now this is comparatively an exaggerated angle, okay, but just imagine theta is small. So if theta is small, then this spring getting compressed will apply a force kx like this, and this spring getting extended will also apply a force kx like this. Now you can see the amount by which the springs are getting compressed or extended is equal to L theta for small theta. Okay, and this is creating a torque like this. So that is 2kx into the moment arm, which is L cos theta. So that is ml square by 3 alpha. Yeah, no, that's okay. I mean, there is a type of problem called a hybrid pendulum where both gravity and spring force are together creating torque. Okay, but that would be in a situation where G is along the rod in the equilibrium position. This is a situation where G is into the plane. So just you have to be careful about which one way. Okay, so now alpha is minus d2 theta by dt square. Okay, x we are approximating as L theta, and cos theta we will approximate as 1. Okay, because theta is small. So these are the small angle approximations that we'll apply here. So having applied these approximations, we will see, we'll get the equation as minus ml square by 3 d2 theta by dt square is becoming 2kl square theta. Okay. So I'm getting d2 theta by dt square as minus 6k by m into theta. Okay, so hope this is clear, people. So these are various types of pendulums. So with this, we are more or less done with the theory part of simple harmonic motion. Couple of things more, of course, we will discuss, like combination of SHMs and also damped oscillations. But before that, I want to come back to some more variations of simple harmonic motion as opposed to angular harmonic motion and understand those variations. Okay. So simple harmonic motion. Displaced mean position. Variation. Let's understand this one first. So standard SHM is of this type: x is equal to a sine omega t plus 5, where we understand that the mean position is basically the origin, and at x equal to x, there's a force of minus kx, where k is m omega square. Okay, so that is the standard type of SHM that we have derived and understood in detail. Okay, so if this is my x equal to 0, at this position, the acceleration should be 0. But the moment I give it some displacement on this side, for example, there will be acceleration on this direction, or if I give it a displacement in this direction, then there'll be acceleration in this direction, and that acceleration is minus omega square x. But now we have an SHM with mean position at x equal to x naught instead. Okay. So just a question of your reference frame has changed, or the origin of your reference frame has changed. So at x equal to x naught, acceleration is 0. This is the mean. Okay. But when we take it this side to x equal to, let's say, x naught plus delta x, then it should have an acceleration like this. Okay. And when we take it this side to x equal to x naught minus delta x, then it should have an acceleration of again. Okay. So it will be written like this because here delta x is a negative quantity. So in this case, delta x is negative, E becomes positive. Whereas here, delta x is positive, E is negative. So how does this equation look like? Let's understand. Okay. So what is happening here is that if you look at the equation, E, which is d2x by dt square, is equal to minus omega squared delta x, and delta x is what it is, x minus x naught. This is the dynamical equation, and this will correspond to x becoming plus 5. Okay. Whereas here, what is happening is that d2x by dt square is minus omega square x. So x becomes e sine omega t plus 5. Okay. So I'll very quickly take you through this derivation from this step to this step also, but just make a note of this also first. So of course, you can say that why there is a need to do this, because we can always take a different variable like s or y or something, where the origin for that variable is at the position x naught. And that's true, you can always do that. But sometimes Doing that becomes lengthier, and it's easier to just write an alternate form of SHM, where the equation of SHM is written in such a way that the mean position already is not 0, but it is x equal to x naught. Okay, so let's see how this equation works out. Basically, that so if we have the condition that on solving the free body diagram or the dynamics, we are getting this relation that d2x by dt square is minus omega square of not x but x minus some term like this, or it is minus omega square x plus some constant, where that constant you can see is omega square x naught. So suppose we get this condition. So what we can do here is we can substitute s as x minus x naught. So d2s by dt square is d2x by dt square. So the above equation, this one, this actually becomes d2s by dt square is minus omega square s. So this equation now tells me that okay, s is equal to e sine omega t plus 5, and then therefore from the above equation x is equal to s plus x naught. That means x as a function of time is x naught plus e sine omega t plus 5. So this is the simple proof of this, that if we have an equation which is of this type, that d2x by dt square is not minus omega square x, but it's got minus omega square x plus some constant term, and it's still an SHM, but it's got a displaced equilibrium, okay, where you can see that x naught is c by omega square. Whatever this constant is, it was that divided by c. That constant divided by omega square. So we'll see how this simple, mathematical manipulation, you can say, it can make life very simple for certain types of questions, where otherwise you would have to first locate the equilibrium position, reorient your coordinate system, put that as the origin and all that. So all that will not be necessary. We can start with this as our basic equation, that d2x by dt square is minus of omega square x plus some constant. So this is like an additional trick I'm teaching you for, particularly for tricky JEE Advanced type of questions. Okay, so let's see how we can put this in use in a practical situation. So we got just a moment, just a moment, people. I'll have to reshare that file. Okay, so we've got this system here where both the pulleys are massless ideal pulleys. Okay, we've got a spring of constant K attached here. We've got a block of mass M. Both pulleys are smooth and massless. We want to find the time period for the vertical oscillations. So here the thing is that we don't need to first find the equilibrium position and all that. What we just need to understand is that if the spring develops a tension Kx, then the tension in the thread is Kx by 2. Okay, and the equation of motion for this block is that mg minus t is equal to ma. Okay. Now the constraint relation here, if the block has a downward displacement s, then the spring will stretch by how much? It will stretch by x by 2. So that you can easily understand that delta x is equal to s by 2. If the spring stretches from x to x plus delta x, then the block will move down by 2s. So it will move down by s is equal to 2 delta x. Of the block. Okay. So here, you can see that mg minus kx by 2 is equal to ma. And we can write E as d2s by dt square. And that becomes 2 times d2s by dt square. So we have the relation that d2x by dt square is equal to minus k by 4mx plus, what is the term now, g by 2. So this is an equation of this type, that d2x by dt square is minus omega square x plus c. So x will be equal to a sine omega t plus 5 plus x naught, where x naught is equal to c by omega square. So x here will be some amplitude plus, now you can see x naught will be this term divided by this omega square. So it will become 2mg by k. Now we can even find the value of x as a function of time if we are given some initial conditions and all. So additionally, we can see that this is an SHM with time period equal to 2 pi by omega. So that now suppose given additionally that the spring constant is 10 newtons per centimeter, okay, and mass of the block is 2.5 kg, okay, and also given that initially at t equal to 0 the block is released from rest with the spring relaxed at natural length and the thread taut. So the thread is taut means the moment you release the block, the tension in the string develops. It does not go into free fall or anything. So from this we will also now find the time period equation of x versus t and maximum extension of the spring. All these things we have to find out. Okay. So now for us, all that is remaining is to find the amplitude in the phase constant. Omega we have found out, and that constant term also we know 2mg by k. So it's half a centimeter. So x is some amplitude into sine omega t plus 5 plus half a centimeter plus 0.5 centimeters. Oh, sorry, plus 5 centimeters, not half. Take the value of g as 10. Okay, so now let's understand how we will calculate the amplitude and the phase constant. So from these values, you can see here that omega is becoming how much? Square root of k, which is this much, divided by 4m. So it's 10 radians per second, omega. Okay. And that term 2mg by k, that is becoming 5 centimeters. Okay. So we have this. So x is equal to, now we can see that x naught at t equal to 0, the value of x is how much? It is a sine phi plus 2mg by k. Okay. And the value of velocity at t equal to 0 is a omega cos phi. Now this should be 0, that's given, and this should also be 0, that's given. So we have cos phi is 0, and from here we have sin phi must be a negative term. So that means phi is how much? Minus pi by 2. Okay. And therefore minus a plus 2mg by k must be 0. So the amplitude must be 2mg by k, which is 5 centimeters. So my equation of SHM is now like this. X is equal to a sine omega t plus phi plus that x naught. So that x naught term is 2mg by k, which is 5 centimeters. That amplitude is also 2mg by k, which is 5 centimeters. Omega was square root of k by 4m, which was 10 radians per second, and phi is equal to minus pi by 2. So ultimately you will see that x becomes like this. It becomes 5 centimeters into 1 minus cos 10t. So you can see that the maximum extension is 10 centimeters and the minimum is 0. And the time period is 5 by 5 seconds. So this becomes kind of very efficient way of solving these type of questions.
So can you scroll a bit up?
Yeah. Okay, done. Now this question is clear.
Yes.
Later you try this by the regular method which I taught you, where you first find the equilibrium position, then displace it from the equilibrium position, and so take the equilibrium position as the origin of your new coordinate system. But you'll see it's just more lengthy, and ultimately you come to the same conclusion as far as x is concerned. That is. Okay, so this is one little trick in SHM. Now, before we conclude today's lecture, and with that we conclude SHM, I'll be teaching you damped oscillations in the next lecture, because that is a topic which is only for JEE Mains, and there will be no damped oscillation questions in the upcoming major test. We'll pick it up in the next test after that. Okay, so don't worry about damped oscillation. However, superposition of SHMs or combination of SHMs is something we'll quickly look at. So we are looking at this kind of situation, that and x2 is some different amplitude but same angular frequency and having a phase difference. So omega, which is 2 pi f, is common for both x1 and x2. Then we say phi over here is the phase difference between the two SHMs. So now the combination, or you can say superposition, or combination here means overlap of the two SHMs, that results in this. So this becomes a sort of application of trigonometric identities and stuff. Okay. So this derivation that we're going to do next is going to be very important for us later in waves, because we'll see superposition of waves has the similar kind of treatment. Okay. So the first thing we do in this is that we expand this term. So on expanding this term, this becomes A1 sine omega t plus A2 sine omega t cos phi plus A2 cos omega t sine phi. Okay. Next, what we do is we club together these terms which have sine omega t. So A1 plus A2 cos phi is the coefficient we get for sine omega t when we take it common, and similarly A2 sine phi is the coefficient we get when we take cos omega t. Okay. Now keep in mind that A1, A2, and phi, these are constants. Okay. So therefore, this whole term A1 plus A2 cos phi is a constant basically. So we can just write it as a new term P, let's say, which is a constant. And similarly, A2 sine phi is also a new term, which is a constant. So let's write it as Q. It's a different constant. Okay. So this becomes that type of equation. Some constant into sine omega t plus some constant into cos omega t, which we know trigonometrically can be reduced into some net amplitude into sine omega t plus some phase constant. Okay. So this is what our x will be finally. Now we can see that this A net will come in terms of P and Q, and further therefore P and Q substituted in terms of A1, A2, and phi. So A net will be ultimately a function of A1, A2, and phi, or it will depend on the values of the individual amplitudes and also the phase constant phi. And similarly, the net phase constant epsilon will also depend on A1, A2, and the phase difference phi. So we'll do that algebra from this point onwards. Just note down quickly up to here.
So noted.
Right. So now you can see what will be A net in terms of P and Q. It will be root of P square plus Q square. Right. So basically we are using this identity that A sin x plus B cos x can be written as C sine of x plus, let's say, epsilon, where C is going to be root of A square plus B square. Okay. And epsilon is going to be tan inverse of B by A. So this method we had seen long before also when we were, okay. So basically what we do is multiply divide by root of A square plus B square. Now this term you treat it like cos epsilon. So this term becomes sin epsilon. So that's how this term then becomes this. So the same treatment will apply here. So you can see that's how this reduces to this, where now our net amplitude is going to be square root of this constant P whole square plus this constant Q whole square, which in turn is nothing but A1 plus A2 cos phi whole square plus A2 sin phi whole square. So now you'll see something very interesting. This formula is almost like a vector algebra formula, even though this is nothing to do with vectors. It's to do with combination of amplitudes. So over here, this formula is called a phasor addition. Instead of a vector addition, it is called the result of a phasor addition because we are adding two waves which have phase. So their amplitudes add in such a way that the phase also plays a role. And epsilon becomes tan inverse of A2 sin phi divided by E1 plus A2 cos phi, because above here, okay. So now these formulae actually can be represented by what is called a phasor diagram. So instead of memorizing these formulae or going through this entire process, we just understand that if we are adding two waves, adding two SHMs of same frequency but different amplitudes A1 and A2, and having a phase difference of phi, then their superposition results in an SHM which has a net amplitude which is given by this A net. Okay. And that SHM, that resultant SHM, has a phase angle with respect to the first one, which is epsilon. So this is called the phasor diagram. It looks like it's of course exactly same as a vector diagram, but because it's not vector addition here, it is called a phasor diagram for the superposition. So actually on its own, this doesn't have huge importance for SHM. It has more importance when we apply this concept for superposition of waves. In fact, specifically speaking, is called interference of waves, which we'll be doing in the next chapter after SHM. But anyhow, it's a good introduction to that concept over here in SHM. So with this, people, we complete SHM, especially the JEE Advanced portion of SHM. JEE Mains has one small other part, which is damped oscillation, which we'll be discussing in the next lecture, along with doubts and questions further. Okay. And from there onwards, we'll pick up waves after this. So that's it for today's session, people. Wish you all the best. And best of luck for the test coming up on Sunday. Any last moment doubts in SHM, etc., that come up, please send it to me. I will help you out with those.
Thank you,
Okay,
sir.
sir.
Okay.
Thank you, sir. Bye.
Bye, people. Bye.